So here we'll check out part B of number 2 from the 2012 AB exam. This intersection right here is something that we found in part A from on the calculator, and we're going to need that intersection again in part B, so I just didn't want to refine that. I just kind of carried it over from the previous part. But in part B it says the region R is the base of a solid, and for each cross-section of the solid taken perpendicularly to the x-axis, when we remove that we're going to get a square. Right, but did not evaluate, so definitely something you always want to look out for. You like when you see that, an expression involving one or more integrals that gives the volume of the solid. So the solid has a flat base and it's sitting on region R. Now, if we take a cross-section perpendicular to the x-axis, that's flat out telling us to cut down into this solid with a vertical slice. And if we cut down in with a vertical slice and remove that vertical slice, what we end up with is we end up with a square face to that cross-section. Now this cross-section does have a tiny little bit of thickness to it, because if we were able to actually pick this up off the page here and manipulate it, this flat edge right here on the cross-section would have to sit perfectly back down into the flat base of the solid itself. And so we can find what the volume of this one cross-section is. The volume of this one cross-section, since it's a very thin rectangular prism, is just going to be length times width times height. So the volume of this cross-section would be approximated by, let's see, well this thickness here is going to be a tiny, tiny difference in x values. Right, the width of this slice that corresponds to the thickness of our cross-section is going to be given by a tiny difference in x values, and then the height is going to be given by a difference in y values. My bigger y value is at the top of the slice, and as a y value, the top of the slice is y equals natural log of x. So I'm looking at natural log of x minus the smaller y value. The smaller y value is on the x-axis at 0, and since it's a square face, that also happens to be this dimension. So the volume of that cross-section is going to be natural log of x times natural log of x, or natural log of x squared, times the thickness to turn into a volume calculation. The volume of the solid is not going to just be the integral of this, though. If you notice, we have another type of vertical slice to the right of this intersection. So we're going to have to do this one volume calculation in two separate halves and add the results together. So this other half of the solid, if we take a cross-section from it and use the same sort of mindset, this is a pretty bad attempt at drawing it, but it should do the trick. If we have our three-dimensional cross-section, this flat edge is going to have to sit perfectly back down into this flat edge in the base of the solid. So the thickness of this is again delta x. We're looking at delta x right here. Now the height, this dimension on this cross-section, is going to be bigger y value, and the y value right here is y equals 5 minus x. So we're looking at 5 minus x minus the smaller y value. The smaller y value still is 0. Since it's a square, we're looking at that same dimension across the bottom. So the volume of this cross-section is going to end up being approximated by taking 5 minus x, not just 5x, 5 minus x squared times the thickness, delta x. The volume of the solid to the left of this intersection is going to be found by doing the integral of this expression, natural log of x squared. The delta x is going to become a dx, telling us what to integrate with respect to. All slices, all cross-sections that have this set of dimensions are going to range with their x values between the x value of 1 and the x value of 3.693. And then the volume of the solid to the right of that intersection is going to be found by integrating the volume of this one cross-section, which is given by 5 minus x. It's got to be squared. The delta x becomes a dx again. And then what x values do cross-sections over here range between? Well, the first x value that's going to give a slice of this nature is going to be at this x value. So our lower limit is 3.693, and our upper limit is this x value, which is going to be the x-intercept of this line, which you can figure out is 5. So what's the volume of the solid that's described here? Well, the volume of the solid that's described is going to be the sum of these two integrals. So we're going to take the first integral from 1 to 3.693 with respect to x plus that next integral. And if you add together these two individual volume computations, you're going to have the volume of the solid that's described. You did not have the option to change the orientation of your slice and use horizontal slices here to get away with doing a single integral because of this phrase in part B. Each cross-section perpendicular to the x-axis flat out tells us we have to cut down into this solid perpendicularly to the x-axis and use a vertical slice. Doesn't ask us to evaluate this, so there it is.